Hello, community. So great that you are back. Today we talk about a new AI architecture. We leave the transformer architecture network behind us and we look at a new form of a neural graph structure. We have two new publications here, as you see from June 26th about hierarchical reasoning model. But at first we have to go to this publication by Meta and Stanford University, published today, June 30th. And here we have our authors, and I always love if they see in their emails that they still, imagine they're at Stanford University and Meta, but they stick to their Gmail account and their Outlook account. I'm just loving it. So let's have a look what they show us here, Stanford and Meta. They have the idea of scaling out instead of scaling up our models. So the network here in this case is not told what to do. So it is kind of a neural network specialization done by its own on the training. They say that inspired by society of mind, beautiful, different models evolve into different experts here for different tasks. And this opens here the door for a more modular, robust, and even more composable AI system in the future. So let's have a look at the latest research. They want to say we want to have a network, it's a graph, you know this, to allocate our computational resources dynamically. So when they show this here on two different parts, and at first we have an image and then we have a text example. Well, let's have a little bit of a deep dive. Distributed neural architectures. And they say, you know what, if we get rid of the layer structure in our transformer and we just define a proto-architecture. So we just have a collection of computational modules. And this can be anything here from a transformer block, an attention block, MLPs, and intelligent routers. So modules and routers. And each token now, so yes, we are back to our next token prediction, is now independently routed through its specific collection of modules, creating here a computational path tailored for its specific context and content. And this path idea, yes, we are here in a graph idea, is of course here in mathematical ensemble theory, in graph theory, and you get an idea where we're moving with this. So the network now has to learn, and it learns how to route here single tokens and what each module should specialize in given the particular training dataset, all through here a standard end-to-end training. Now, the big hope is that by analyzing the complexity and the structure of the path in a higher dimensional manifold that each single token takes, the authors hope to understand here kind of the reasoning process, but this is not a step that they officially take, but it is, it is in the background. So their paper shows now that certain path becomes specialized and specialized for general concept, but also specialized for high-level concepts. Now, one of those examples, a mixture of expert system. No? This is a prime classical example. Yeah? Therefore, different tokens or different patches are allowed to take different paths through the network. And each path is decided by an additional structure called the router in the mixture of expert system. Yeah? This is kind of, if you want, a main application of conditional computing, CC, is to partially decouple the parameter count and compute by activating only a fraction of the parameter for each forward pass. But we are now moving beyond forward pass. So what the authors here did, Stanford University and Meta, they trained two types of models. And they said, listen, we want to examine if our idea holds true in vision, in the vision domain. So we go with an ImageNet from 2009, so really famous. And we want to have a look if it's hold also for a language task. So they go here with a FindWebEdu subset here. Beautiful. Let's examine. Now, if you want to understand this proto-architecture of a distributed neural architecture, we have more or less some simple component structure. No? We have an input node, we have an output node, great. And then in between, as I told you, we only have more or less distinct computational modules, whatever we design those models to be. And we have routers that learn, given the pre-training data, how to decide where to route which token to which module. And this is it. As you see from a mathematical perspective, this is just an optimization task. And these are our elements that we optimize here in a given framework. So each computational module, I think this is the most important element here, operates here on sequences and can be a transformer, MLP, an attention block, a mamba block, convolution, any other operation. And I think this is the beauty of this idea. You are not fixed on operator, a mamba structure, or whatever, mixture of expert, but you just combine them and say, yes, I provide everything of the ecosystem that we know in AI now as a module, and the system is self-optimizing here, is finding here a graph configuration given the pre-training data for a particular task that I as a human user have here during the inference run. How do they do this? I call it a simple trick. So you see, if you want to understand where this is coming from, I imagine this also, it's just trying to implement a mixture of expert system and a mixture of depth at the same time. This is more or less, if you want to understand here, from familiar technical terms. Ne? In case each token skips here an MLP block as well as certain transformer block leading here to different token following pulse or different lengths. And if you're not familiar, this is here the study. This is here from April 2024, of course, by Google. Who else? Ne? Mixture of depth, dynamically allocating compute in transformer-based language model. And they already had here this idea. We don't want here to waste energy or waste time running here through each and every layer. Can we dynamically here compute here specific position in a sequence, therefore optimizing the allocation along the sequence for different layer across the model depth? So they already started here to look at the layers and say, hey, maybe we don't need all the layers. Maybe we don't have to compute through all the layers. Maybe we can activate, deactivate, optimize. So they already kind of had this flexible idea of the layer construct in a transformer block. Great. If you are interested in this study, look especially here at figure 1, this mixture of expert depth transformer architecture. I think it gives you here a beautiful understanding if you use here the sequence and the different layers on the routing decision, and you understand here how here even an energy optimization is performed. And we just combine this now with a mixture of expert, but there's one idea that I have to tell you, and you know what? As a subscriber of my channel, you know, of course, skip connection. Skip connection is a familiar term, but now they also introduce here the identity models, which simply pass the token through without any computation. And you might say, why? But think about it. We are here trying also to optimize here the runtime, reduce energy, reduce timing. So absolute natural that we also go here in this new neural graph structure with a skip connection. But a skip connection is not that easy because you have to have a clever trick up your sleeves. And I think this is here where the DeepSeek V2 paper is here beautifully showing here how to implement this. Now, if you're not familiar, DeepSeek AI here, mid of June 24, DeepSeek version 2, and they here looked here in particular at a lot of new methodologies, let's call it this way. So if you're not familiar, have a look at the paper, you will learn a lot of. And, you know, they say, hey, how can we encourage your model to use here the skip module without inferring here with its primary training? Because the primary training is, hey, we want to get better and better. No? We want to optimize. We want to reduce here our loss. We have a given loss function. And the standard way was how we can integrate here a skip model here. If we have multiple objectives, we just add a penalty term to our particular loss function. This is in a very simple case possible, but you know what? They found here DeepSeek AI, and congratulations to their paper, a bias trick. It's a kind of a trick, it's a methodology, or whatever you like to call it. It simply sidesteps all those problems here of multiple objectives here in parallel at the same time by entirely creating here a separate, simple control system that operates now outside here of the main gradient-based learning loop. And the idea is that the bias here that we introduce is not updated via backpropagation. It is updated at the end of each training step using a simple handwritten rule. And you find all the information here in the paper here by DeepSeek. Now, they used it careful. You have to understand it a little bit deeper. They used it here for a different purpose. And they used it for load balancing in a mixture of expert model, because they have here a mixture of expert model. Ne? So their load balancing was their ignite to come up with this idea. And now Stanford and Meta use this idea here. They cleverly repurpose, this load balancing idea and implementation. They saw this is effective here in DeepSeek. They adapted it to manage the load now of one specific type of module. And yes, this is exactly the identity module to enforce here a computational budget. So I always like this transfer of knowledge between the paper. And if you read the paper and you're a little bit familiar with what happened in the last month or in the last year, you immediately see it's not always a brand new idea, but it's a combination of known facts, or maybe here a cleverly repurpose action here, where I say, hey, this worked at load balancing. Now I just need it for one module, but I can use this because, hey, that's fast and effective. So really love it. Have a look at the papers. This is here the main paper, Stanford University and Meta, and they tell us now. And I show you here the example, and it's always good to have here visuals. So we have here 3 images, and let's start with the image before we go to language. So they highlight here the paths of different patches taken through here the network. And you see here this bird, and then you see here the highlight of the path structure. So yes, you can see, for example, here in blue, you have more or less here the, let's call it the outside of the bird and the little branch here in blue. And then here the body of this little bird is here in green. So you see, yeah, there is something we can identify. It's a little bit harder on this. You see here geometric patterns on those two and on those two. And you also hear the shape of the fox. You see here the shape of the fox, the fur of the fox here. So this is interesting, yeah? The authors say we see very clearly emergent specialization of path. Some paths focus on the object, like here, I think with fox, you see it really nice. Others on the background, and others on the edges, and others on the boundary. So we just have a visual primary task, if you want, from separation and segmentation. And they say this visualization also illustrates here the sparse nature of the attention. Patches of different colors do not attend to each other in later steps of the forward process. But remember, I told you we want to go beyond simply a simple forward process. So here we have now this new idea. We have here our different modules, whatever it is. And as I showed you here, the identity module that we just learned here, the simple bias trick from DeepSeek version 2, is also now, if you want, kind of a model. If we decide, hey, we don't have to continue to process this and use a computational infrastructure, we already have kind of a solution. We don't want to waste energy, waste time, waste money. So those are here the single black dots. Yeah, and if you want, you see this here from a token perspective. The forward pass consists here of a series of steps. At any step, each token is acted on by a single module or by an identity operation. Here, these are black dots. When a module that contains attention operation acts on several tokens simultaneously, the attention pattern is computed, and you see this below, only on those tokens. Great. Now you know, and I was interested, what is the performance of the system? Great, so you have a new architecture, you have a new graph network now, you got rid of layers, or maybe you have a liquid layer configuration. But what about the performance? Tell me the performance compared to a vision transformer. And in blue, you have the classical vision transformer. And in green and in orange, you have now this new methodology for k equal 1 and k equal 2. And they argue, yeah, it's almost as perfect as the vision transformer model there, the rigid layer structure. And okay, yeah, great. This is here. Okay, the first indication. So it is maybe not as good as you compare it to the blue line, but they're coming close, given enough here steps, beautifully. Now, the real interesting part is if we look now at the pathway itself. So here we have now a top 1, and as you see, we have a router here, given here from 1 to, I don't know, 1, 2, 3, 4, 5, let's say 10, and we have here 17 modules here in each column. And now the interesting thing is in the first part, and we are here in the vision part, so we have here an image network, we have an input, beautiful. And then from all the modules here and the little circles, so here the module and the size of a circle gives you the frequency of the activation of this module here. You see there is here not, as you see here, a complete matrix, no? This is a single linear path. So here you see in the first half, we have more or less here a highway. The system knows exactly what to do. There is no open decision. If you think this as a decision-making machine, hey, we found our modules that we have a linear sequence of model that we operate. And only in the second part it gets really interesting. So vision for a top 1, a k equal 1, or a decisive router that has only one option to take. This is quite interesting. So the model has learned here that initial processing, like in identifying edges or going for colors or going for textures, is universal and should be applied to everything. This is here if you want the dense backbone. If you go back, this is here the highway. Edges, color, fur, I don't know, surrounding, identify. This is a standard way of procedure that we do. There's not a lot of learning happening here in this simple case. In the second half, the pattern changes now dramatically. The traffic spread out here between our columns here of modules. First, the circles itself become smaller and more numerous. So this means after the initial shared processing, the tokens now begin to follow diverse specialized paths. And the network becomes now a collection of specialized sub-networks. This is really nice. You see here, it's branching out. There's a lot of, you have here main path forward, but you also have here in little gray a lot of connectivity between those smaller dots. So this is interesting here. You see that now a multitude of paths emerge for particular tasks. But you say this is easy, no? This is for k equal 1. This is a top 1 graph implementation where we only have one router that does here the calculation. But what happens here if we say now the router calculates the score for all modules and selects now 2 modules with the highest probability? Because remember, we are still in the next token prediction. We are still operating with probability distribution. We just get rid of the rigid structure of layers, but everything else is still there. And even if I have a transformer block or a mamba block or a feed-forward block or MLP block or whatever, we are still operating here with probabilities. Okay, so next case is now after 1, you guessed it, 2. So the router now calculates the score for all modules and selects now the best 2 modules with the highest probabilities. Great. So here we have now the path. Now it's interesting. You see in the first half, we still see those highways coming up, no? Those ways where this is the way to go. But we have now, if you compare it here to this one, we have more of, if you think about a highway, there are the little towns, these are the side street, the back streets here, where I say, hey, maybe not stay on the highway, maybe we visit here this little town. This is specialized in, color identification, and this here is specialized in boundary detection, and this is here in segmentation of, whatever object we want. So you see, maybe not just stay on the highway, but diverge a little bit our path structure. And this is happening here in part 1. 2 in the first half, but even more in the second half. Now, computational path, a token no longer follows here a simple path. It traverses here to a ribbon of computation. We talk about this. This comes here from mathematical ensemble theory. And the journey is now a sequence of pair of modules because we have now, if you want 2 modules that are taken here, module 7 and module 2 and module 9 and module 1, whatever combination you have. If you want to imagine this, I have an analogon. Think about you are traveling somewhere and you are standing here at a crossroad and you send out 2 scouts down the 2 most promising roads. And the scouts go there, these are your models, and the scouts report back. And then you can combine their findings. You see, okay, if I take model 1, I achieve this. If I go the route of model 2, I achieve this. You decide then on the next set of crossroads to explore. Rather simple idea. In the implementation, it is not that easy. And because we want to save compute time, we have now to integrate the skip model approach. Means the model has learned that for certain tokens at certain stages, the best action is now to do nothing because you have achieved your goal and just save the compute time, save the compute energy, and save the compute infrastructure. Do not burden the system further. So interesting if you see this, and here you have a 25% skip module integrated here. But this was vision. Vision is nice, but we humans, no, we want to know about, at first, human language, and then about reasoning, because we reason not in vision, but we reason in the human language. Now here you see exactly the same now for language. Now the authors decided here, do I have this here? Yes, I have it here. To go with, this is Meta, no, Meta is here a global corporation with millions of GPU. So they decided they run their research on a GPT-2 system. Which is, I mean, I understand. You don't want as a corporation to show here your competitors, no? If we use here, this is the base for the next Llama 5 system, no? So we take here a GPT-2 system with 406 million trainable parameters, beautiful. And you see here the loss function, yeah? So, and this is the blue one. So GPT-2 is here, really good, really good. GPT-2 is here, the lowest loss, yeah? But here something happens, no? Here the green, the top 2 DNA comes in, no? It's a little bit bigger, 433 million free trainable parameters, no? And this is now that we can claim here at Meta. The most crucial finding is that here with this new architecture, it achieves here the lowest validation loss, outperforming here a GPT-2. Well, okay. I don't know how you see this, but okay. It outperformed a GPT-2. Anyway, from a theoretical perspective, this is interesting because this means it kind of works also here if we apply it here to language token. Now, GPT-2, I think also, if you have an industrial, I mean, Meta should have a research lab with more than 5 GPUs, but okay, I mean, they would have gone with a Llama 3 model, or a Llama 4 model, and no. Okay, whatever. Just look at the patterns here that we see. Look at the different paths. Now the paths become really different to vision. Vision is simple, language is difficult. I have here in detailed here the top one distributed neural architecture here that we are discussing. We have 35 modules here in each column if you want. And here you see now the steps. We have on the left side the input and on the right side the output. And these are now the highways for the classical simple task. And then you see a dense network of paths. You can even distinguish between them for each more complex task. So the complexity of a task is now given here, complexity in the path, given that this is here our hypermanifold that we can operate and connect on and with. They decided here to go with 36 modules, beautiful. But if you go now to top 2, the k equal 2, so we have 2 modules, the situation becomes now really crazy. So we have here module 0 to model 71. And now look here, and I think we can really say we have now a continuously distributed routing pattern in front of us. There are, I don't know how many thousand and 10 of thousand of of paths connecting now here the input and the output. We are not talking about reasoning yet. And this top 2 router effectively has, if I'm correct, more than 2,500 unique dual module operation it can apply at each step. So you see there is enough variety how to encode here the token embeddings, the complexity of the human language, of the human words in specific contexts. So I think this is a very interesting approach, and it's a very simple approach. Remember, each of those little dots can be either a complete transformer block or maybe just the attention block, or maybe just the feed forward block. And the system learns this configuration. And when it is given a task in inference time, then it just activates here a specific pathway through. And it does not run through all the layers and all the path of all the layers in a classical transformer. This is only for experts. Skip it. It's not really that important, but I had a look at the effective routing diversity. So this is kind of a measure of a concentration versus the distribution of token traffic across the modules. No? It is calculating using here an inverse participation ratio that we know here from physics, and that is used to measure how localized or how spread out a quantity is. So if we take k equal 1, now this is here the orange one. So, and we have here the number of steps. You see, it is almost, there's some peaks, but forget about the peaks. It is a lot of the time, it is really at 1. No? Look at this, here, 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 over there. So what does it mean? It means that the routing is perfectly concentrated. 100% of the token at that step are being routed to a single module that's specialized for this particular token. The network now is behaving in a classical way that we know it, like a dense feed-forward layer. Now, if we increase now here the value, stays not at 1, but diverges a little bit, we start to have a non-uniform distribution. No? You remember, lower value means here the traffic is concentrated on a few highway modules, as they call it, while a higher value means the traffic is more evenly distributed among many models. Now, this is on the one hand what we want. No? We want to have distributed computing. We want to have a lot of possible models, and we want to use here the diversity of those computational models for solving our task. But this also comes with kind of a drawback. No? And here in green now, if we go to k equal 2, the green, you see, you hardly touch here the one line at all. You are not there at all. So this means now different path. It distributes now the computational load of the task more evenly across all the expert modules, quotation mark, in the later stages, rather than concentrating it on a few. So this now is a good indication if you go here with this inverse participation ratio, because it implies here a more collaborative and a less hierarchical process strategy is indeed learned for the human language by this neural graph architecture. A little bit complicated, never mind. This is it. This was the paper. But at the end, I have some personal reflection and some personal thoughts. Now, at first, I did not understand what exactly is this module. And then I understand it is more or less a standard transformer block. No? Contains here the self-attention sublayer and a feed-forward network sublayer. Great. But in the appendix of the paper, and have a look at figure 21, you see that they explore even here on a finer grained specialization. So they say, okay, but we know that the transformer block, we can subdivide it further. Yeah? We can go now for the attention part of the transformer block, and then we go with the feed-forward MLP part of the transformer block. And they examined this, and I think this is absolutely beautiful, because look at the result here of the paper. So in green, you have MLPs, and in orange, you have the pure attention of the blocks. And now we have the same here. We have our input and our output function. And you see, this is here for visual. You see also we have now, again, our highways. But you see the distribution between our pure attention calculation sublayers and the MLP sublayers is now really interesting. Look at this particular pattern in the first half. And then we have here kind of a coherent system also in the second part here. So this is something that I like, and doing some experiments, because this can have implementation I explain later. And then I ask, hey, what is happening in the training process and what is happening after the training process? So those are my thoughts, and maybe I'm completely wrong. So please, if you find out that I made a mistake, just comment here to the video. So the way I understand the training or the specialization process here of the graph structure is, the router starts sending different types of tokens to different modules. No? Let's say by chance module 7 starts receiving here a lot of the punctuation tokens. No? Question mark, exclamation mark, whatever. And we're still here that the overall goal of these sub-layers are to minimize the prediction loss, even in a graph. No? And through backpropagation, the weights, the parameter inside the model 7 will be now updated specifically to get better at processing here those specific punctuation token in a way that helps now in the final prediction task. And this happens here, let's say in module 7, but in module 15 you might go and specialize on verbs, or module 22 you go on nouns, So there's now a spontaneous symmetry breaking happening here in those graph structure, but no, it is just by accidents that some models here specialize. Now, what has happened here after the training? No? What is this emergent, or this development of an expertise of one model? No? And I think after millions and millions of targeted updates now, the internal parameters here of module 7 are now highly fine-tuned for handling all the punctuation tokens. No? So from the architectural point of view, it is still a standard transformer block, but it has now really been pre-trained to become this punctuation expert model. If we want to compare it with mixture of expert model. Ne? Module 15 has become a verb expert and so on. So in my understanding, you really do not start with a predefined system. You don't condition the system. The expertise is not designed in. It kind of emerges as a result of a dynamic routing and of an optimization process. Now, how you start this process and what you already give as a predefinition in this proto-architecture type is, of course, of interest. Yeah? But more about this later. Yeah? And my understanding is that the router learns who to send or what to send where, and the modules learn to become good at what they are sent. So this is an absolute interesting approach. You say, I get rid of this rigid layer structure, and given the complexity of my task that I have to do, given the human instruction, yeah, I know from my pre-training data, given here this specific task in this specific domain with a specific complexity, with some specific context, then I know there's path number 4,370,020,000, whatever, and this is the successful path I have to go now in this free-floating graph structure network of modules. Okay, I like this idea. Very short summary. So how does it work? At a given step, S, the token embedding at the very beginning now is fed here to a router R. The router computes its logic, classical, performs a classical softmax function to produce here a probability distribution over all available modules MI. And then the routing decision is made. No? The authors here of the paper from Meta explores here a top K routing, K equal 1 or K equal 2, I showed you both figures, where the token is sent to K modules with the highest probability. So K equal 1, each token here follows a single path, classic. But the really interesting thing is for K greater than 1, no? Because now it follows a ribbon of path, and this is ensemble theory, and I don't know how good you are in mathematics, but now it gets interesting. K equal 2 is still understandable. K equal 4 is just that my brain explodes. So, nice thing. Yeah, and then the selected model process here, the token embedding and the output are combined to produce the next stage, and here the cycle, the loop starts all over again. Now we understand the mechanism. We also understand, looking at the graph, that this new architecture, this distributed neural architecture, the results produced with this architecture are not better at reasoning at all. Think about it. Reasoning is still, in the classical way, in the transformer way, a function of some scale, of immense scale. And those small, bigger is better, were intentionally kept small in this study by Meta to prove here, just the first step, the architectural concept here, is it possible at all? So they were compared it to GPT-2, so you get the idea. With the focus only in the architecture, they were not optimizing here for performance, but maybe for Llama 5 they have an idea, who knows? And they showed here, and this is the important thing, it works, this mechanism, for vision and for language. And I think if it works for vision, it works for video, and if it works for language, it might work here for reasoning optimization, which they did not cover in the paper. However, there's a reason for this. Think about it. This mechanism that we just explored is more or less local. No? It is a stepping stone towards more complex system that could one day in the future perform here some latent space reasoning, but we are not there yet, not at all. Why? Because even this dynamic, maybe even you can call it adaptive routing, in the current distribution neural architecture implementation is based on the local state of a single token. We are still attached to this unholy idea, I have to predict only the very next token. My goodness. No? So the router now asks at step whatever, hey, based on my current embedding, no, where should I go next? And if you want, this is a form of a local reactive decision making. But this decision making that is so local and reactive is not really reasoning. At least not the reasoning that I need for science. Because in my crazy little mind, I think that complex reasoning requires at least some of those ideas, like a global planning process, some iterative refinements, some working memory, some global scratchpad of information, of knowledge, adaptation, context to the external world, the ability to learn from feedback from the external world, and so on. But anyway, this study was absolutely fascinating because it gives us here two new insights. To handle general high-frequency features, the simple stuff that people want AI to do, there are now the development, as we can see, from very few common highway paths that a majority of tokens take. So these are established routines. This is exactly, we know how to do it, how to handle it. We have our, if you want, known highway path. The story gets really interesting if we have some specific nuanced complex inputs, because then those highway paths are useless. So then in the pre-training of the model, there must have been such an amount of thousands and millions of examples of higher complexity tasks, so that a model could learn on those examples, could integrate this functional knowledge here in its neural graph structure, that a path emerged in the training process. And now, in the inference run, when I now approach this system and I have a complex query, in the training data, there must have been a very similar task to my query today, where the system learned that there is a highly specialized path with all the modules and the sequence of parallel activation of modules and whatever. But this is a very rare, this is a very unique path. And if you have not done the training in this high complexity hyperplane, you will have no reasoning capabilities for more complex input, even in this new AI architecture. I think it was an absolute fascinating paper. I love the paper. Great work done. Absolutely fascinating. Eliminating the layers. Have a look at a new fluid AI architecture coming up. And yes, there was another paper at the very beginning of this video. Yeah, I think we leave this interesting paper then for the next time.